Um, so we've all experienced the situation where for example, on a cart or on a train, and we're moving forward with some velocity, say 5 meters per second, and we're going along, and life is good, and then we then are in a situation where someone else is viewing us, and the train itself is moving with a velocity of, say, 2 meters per second. So now there are kind of two frames of reference. There's the frame of reference of the train, and there's the frame of reference of the Earth. Does that make sense? And the question now becomes, what are the velocities of the different objects relative to their frame of reference? So I think the simplest way to think about this is to start by looking at the frame of reference of the train. And so what I'm going to do is I'm going to write the position of the man with respect to the train is this right here. He starts out man with respect to train. He starts out right there. Does that make sense? And then there's a frame of reference of where is the train with respect to the Earth. Train with respect to Earth. Is that clear? And so if I want to know what the position of the man is with respect to the Earth, what would that look like? Anybody got any ideas what that would look like? So man with respect, the position of the man with respect to the Earth. Like how far is he from the origin? It's going to be the position of the man with respect to the train plus the position of the train with respect to the Earth. And then if I want to know relative velocity, if I have position, how do I get velocity? What's velocity equal to? It would be the derivative, right? So if I take the derivative of the derivative of man / Earth position with respect to time is equal to the derivative of the man with respect to the train as a function of t plus the derivative of the train with respect to the Earth. With respect the position of the man, the train with respect to the Earth as it changes over time. And so, real simply, the velocity of the man with respect to the Earth is equal to the velocity of the man with respect to the train plus the velocity of the train with respect to the Earth. And it's a pain to have to be so formal, but this man with respect to Earth, man with respect to train, train with respect to Earth. And I like to think about the fact that if you had a fraction of m over t times t over e, you'd end up with m over e. Does that make sense? Yeah. Let's imagine you're on a train, and you're walking forward in the train at 5 meters per second. So you're going, that's you. The train itself is moving at 2 meters per second. So the velocity of the man relative to the Earth is going to be man to train, 5 meters per second, plus train to Earth, 2 meters. So let's just rewrite that equation. Velocity of man relative to Earth is equal to velocity of man relative to train, velocity of train relative to Earth. So suppose I'm looking at a ball being tossed on a bus, and from the frame of reference, so ball tossed on bus from side of road, I see 30 meter per second ball velocity. So coming back to this equation, I'm just going to rewrite it for the case of a ball. Velocity of ball with respect to the Earth is equal to velocity of ball with respect to I'm going to call it a truck just so that the symbols are simple, plus velocity of truck with respect to Earth. And so in this case, which number is this 30 meters per second? Which of these three variables is at 30 meters per second? Which one would it, yeah. So it's ball with respect to Earth. So I know that 30 meters per second is equal to how fast the ball was going with respect to the Earth. And I know that the ball, I'm going to give you the ball with respect to the truck is 7 meters per second. So that would be 7 meters per second. And now I can ask the question, what would the velocity of the bus or the truck be with respect to the Earth? So how fast, if I see a ball moving at 30 meters per second, I know it was thrown with a velocity of 7 meters per second. How fast must the vehicle be going? Yep. So it'd be 23. So V of the truck with respect to the Earth is 23 meters per second. So it's kind of, I think it's a pain to have to be so formal, but I think it's the way that keeps you out of trouble. Yep.
Can you say again where you got 7 meters?
I gave, that's a great question. This was a given. So that's a given, and that's a given. And what I solved for was, that was my unknown. Yep. What I did was, I didn't want to, that's a great question. I didn't, because I had ball already for B. I decided to make the bus a truck. Just to keep it more straightforward. Okay. Yep. Ask your question. So if you're on the train, so the idea here would be if you were on the bus or the train or the truck, you would see a ball going back and forth at 7 meters per second.
Okay.
So you're on.
What's the 30 meters per second?
That's you standing on the side of the road. That's what you see when you look from the side of the road.
So then what's the 7 meters per second?
If you were on the bus, that's what you would see.
Oh.
Is that clear? Clearer now?
Yes.
Okay. So the idea here is that if you're in the frame of reference of the truck, you see 7 meters per second. If you're in the frame of reference of the Earth, you see the ball moving at 30 meters per second. Okay, so let's imagine a slightly different scenario. Still same equation, and this time we're going to do a boat, B for boat, with respect to the Earth is equal to velocity of the boat with respect to the water plus velocity of the water with respect to Earth. So these show up at kind of in two situations. One is that problem that I showed you of, you've got a current that you're fighting or a tide that you're fighting, and the way you'll see it initially is typically going to be that you're out on some open water, and perhaps you're headed in this direction, and you can paddle. The velocity of the boat with respect to the water is, say, 4 knots. A knot is a nautical mile per hour. And it actually comes from the fact that in the old days, to see how fast the boat was going, they would take a long rope with a bunch of knots in it, and they would just feed the rope overboard so the rope stayed stationary with the water, and they would measure how fast the knots were going over the edge of the boat. And let's imagine that there is a current in the water, which is at 3 knots due south. So I point my boat at 4 knots to the east. Current takes me 3 knots to the south, and I want to know where am I going to end up long term. So now we have to take into account the fact that these are vectors, and so what I'll write is the velocity of the boat with respect to the Earth is equal to velocity of the boat with respect to the water in the x direction plus velocity of the water with respect to Earth in the x direction, I hat, plus velocity of the boat with respect to water in the y direction, velocity of the water with respect to Earth in the y direction, j hat. And I'm given both of these values. This is going to be velocity of the water with respect to Earth. So I can plug numbers in here. I'm just going to make a note that as a vector, this looks like 4 knots to the x means I hat. And this looks like 3 knots minus 3 knots j hat. Is that clear? Right, because it's going south. It's going south, so it's minus y direction. Just because it's worth doing, I'm going to write velocity of the boat with respect to water in the y direction is 0, and velocity of the water with respect to Earth in the y direction, sorry, in the x direction is 0. Let me write that clearer. And now I can just go and plug all of that into here, and I get v boat in the water is equal to velocity of boat with respect to water in the x direction is 4 knots I hat, and then this gives this term over here gives me my minus 3 knots j hat. From that, I could figure out a magnitude of the velocity. What would be the magnitude of my velocity? 5, right? It would be 4 squared. 4 squared plus 3 squared is 5 knots. And my angle would be minus 37 degrees. And I guess there's probably one final point that's worth coming back here and mentioning. This often shows up in when you want to cross a river. So you come to, I have a river. The river is 100 meters wide. I want to cross the river. And I hop in my kayak or canoe, or I'm a swimmer or whatever. I head directly across. The current takes me down. And we can figure out, or how would we figure out how long it takes me to get across? Any ideas? So what would be the time to get across? Yep, Evan?
The distance between the two banks divided by your speed.
So it would be distance in the x direction divided by velocity in the x direction, correct? And so in this case, the distance in the x direction was 100 meters. And velocity in the x direction was 4. I'm actually going to switch to meters per second just because we're now. So the knots and meters are not equivalent, but we're just going to switch over here. And so the time across would be 25 seconds. And where would I end up? Where on the other side of the river, where would I end up? Any ideas? Like, would I end up right across on the other side? Would I start here and end up here? No, where would I end up? Somewhere downstream, right? Because the distance in the y direction is the velocity in the y direction times t. And that's minus, again, switching knots to meters randomly, minus 3 meters per second. Divide times 25 seconds. So I would end up downstream minus 75 meters. Okay, yeah.
Why would it still take you the same amount of time to go different distances?
That's great, because in essence, I move at 4 meters per second, correct? That's what I can do. The river gives me an additional velocity as a vector sum, but you notice if I were to calculate this distance here, this distance, if that's 100, this distance here, 3, 4, 5 triangle, 125 meters. And if I travel at 5 meters per second, the it's still going to take me the same amount of time to go from here to here. I'm going to do one more scenario, then we're going to take a break. And that is, let's suppose same similar situation. Velocity of boat with respect to the water, 4 meters per second. Velocity of the water with respect to the earth, 3 meters per second. But now, I have a waterfall. I have a 20-foot drop. But I need to get across that river. And imagine it's a deep gorge. This is a gorge, so I can only get on the river right here. So what the heck am I going to do? Any ideas, Justin? What do you think?
You're gonna have to paddle upstream.
Right, so a perfect answer. I'm going to go upstream like that, right? And I'm going to let the current take me downstream. Right? So let's put a couple things in here. We know that this here is 3 meters per second minus 3 meters per second j hat, correct? Yep. If we call that angle theta, this is going to look like 4 cosine theta I hat plus 4 sine theta j hat. Everybody agree with that? And in this case, bottom line, I want velocity of the boat relative to the earth in the x direction. I want that to be some number. I don't know what it's going to be, right? But it's going to end up looking like velocity of the boat with respect to the earth in the x direction is going to be velocity of the boat with respect to the water in the x direction plus velocity of the water with respect to earth in the x direction. And that's 0. So this is just going to look like 4 cosine theta. And velocity of the boat with respect to the earth in the y direction is going to be velocity of the boat with respect to water in the y direction plus velocity of the water with respect to earth in the y direction. And what does that have to equal? If I'm going to get across safely, what does that number have to equal? What does the result of this vector and this vector should be a vector that goes directly across, right? I want my resultant vector to be like that. Does that vector have any magnitude in the y direction? No, right? So that has to equal 0. So what I know is that boat with respect to water is going to be plus 4 sine theta. I'll put j hat just to plus minus 3 meters per second j hat equals 0. So the sine of theta has to equal 3/4 or theta. Can somebody tell me what the arc sine of 0.75 is? 48.59 degrees. So that says that I need to put this angle has to be 48.59. And then what does that give me for velocity in the x direction? So the velocity in the x direction is going to be 4 times the cosine of 48.59 degrees. 2.65. And so if the distance in the x direction is 100 meters, the time to get across is the distance in the x divided by the velocity in the x. So what does 100 divided by 2.65 give me? So the time to get across is 37.74 seconds. So it takes more time, but I don't go over the waterfall, which is fortunate.